Daniel Nocera is the Patterson Rockwood Professor of Energy in the Department of Chemistry and Chemical Biology at Harvard University. He's well known for his work on renewable energy. Welcome, Dan.
Hi, thank you, June.
I understand you've developed bacteria able to keep on accumulating nutrients just from sunlight, air, and water. Could you explain a bit to us about that? Most of our listeners aren't scientists.
Sure, but they remember from grade school probably photosynthesis. And so that's one thing photosynthesis does is it accumulates energy from the sun, and then you give the plant water and it breathes in carbon dioxide from the air. And this combination of sunlight, carbon dioxide, and water gives rise to all sorts of things. One being biomass, wood, glucose, food. So we can keep going. So that's what happens in a photosynthetic organism. And that's what powers all of life, is that you're using carbon dioxide from the air, water, and sunlight, and you're literally building the world you see around you. It also gives you oil, which is one problem we have now that we're using so much of it. But it gives rise to almost every product that we live off of, that we eat, that sustains all of life. What we did is we didn't use a leaf to capture light. We used an artificial leaf. And what that does is it catches the sunlight and splits water to hydrogen and oxygen. And then you mentioned the bacteria. We take special bacteria that they eat the hydrogen. That's its only food source. And then breathes in carbon dioxide and does basically photosynthesis. It will take carbon dioxide plus hydrogen and make biomass. I can make food. I can make whatever you want out of it.
Wow, that's really incredible. Can you relate that to the sustainable and decentralized fertilization of crops?
Now you just went one step further. We decided to go one step further than even photosynthesis. And we said, if I just told you that you take hydrogen from solar water splitting and carbon dioxide, and you make carbon-based things like biomass and food. And when I say food, I mean things like glucose, things, sugars, and things like that. But then we went one step further, because what's in the air is nitrogen. And so we asked another organism first to accumulate carbon and hydrogen and make an internal food supply that it could live off of. Sometimes I describe that as a hibernating bear. So that's what hibernating bears do. They eat a lot and then they go into hibernation. And so we make this bacteria. We use solar light, split water to hydrogen, and then we tell it eat a lot of carbon dioxide and hydrogen, and then store it like you're hibernating. Now, once I have the organism loaded up with its own internal food supply, which was driven by the sun, like I said, I can then put the organism in the ground. It doesn't need to see sunlight anymore. It eats its internal food supply and breathes in nitrogen, and it makes fertilizer. So we went one step beyond a photosynthetic organism, and we basically made a photosynthetic organism, or a solar-driven organism, that can then do fertilization of crops. And there it's taking nitrogen from the air and using its internal food supply to power what's called nitrogen fixation and make basically nitrogen fertilizer, and I can grow crops with it. And so that's what we've done. Let me just tell you, the first thing where we just do carbon, like the photosynthetic cycle, we call that the bionic leaf C for carbon. And then the second one, we call it the bionic leaf N, which is for nitrogen fixation to do fertilization.
So, is this actually being used and where?
This has gone really fast. So first off, you could use the bionic leaf seed and make liquid fuels. But the economics of it is you need carbon pricing. And the reason for that is society's built a multi-trillion-dollar infrastructure that is based on coal, oil, and gas. So there's no scientist who's going to invent something to displace a multi-trillion-dollar infrastructure without a thing called carbon pricing. That's why you'll hear other people at Harvard, like Stavens in the Kennedy School, say things like, we need carbon pricing, we need carbon pricing. But for bionic leaf and nitrogen fixation, I've needed no incentives. We're actually making basically this biofertilizer at a cost that's competitive with chemical fertilizer. So that's good news, because that means I don't need any tax incentives. I'm just on the open market and I'm competitive. And that's why we went after fertilizer. And then you could say, yeah, great, but what's fertilizer really doing for climate change? And most people don't realize this, but to make fertilizer globally, you put 900 megatons of carbon dioxide into the atmosphere. Because when you make fertilizer chemically, you use methane as the hydrogen source. And when you take the hydrogen off of methane, you leave CO2. So fertilization puts around anywhere between 2 to 5% of all carbon emissions is due to fertilization, 900 megatons a year. And so if I can avoid making fertilizer without carbon dioxide, which this bug does, I can save a lot of carbon dioxide from going in the air. And we've shown that you can use, for instance, on a field trial we just did in the Central Valley of California, on a 400-acre farm growing lettuce, we saved 150 metric tons of carbon dioxide from going into the air. If you start thinking about it, and this answers your question, is it being used? I'm cost competitive with chemical fertilizer, and I'm saving all this carbon dioxide from going in the air, and I'm not getting algal bloom runoffs because the nitrogen is different than chemical fertilizer. It's used on demand by the plant. So I'm not having a bunch of nitrogen get washed away like you do with chemical fertilizer. It's made this process really economically attractive to lots of people. And so it is being used. I'm going to put a caveat on it. Can you go into Lowe's and buy it right now? And the answer is no, for two reasons. One, it needed to be federally regulated, and I just got cleared by all the regulatory statutes in the United States that it's safe. So I can now use it anywhere. But the real issue is, at the end of the day, a farmer only cares about yield. And so I'm asking a farmer to not do what they've done for 70 years and do something different. And so we need to do lots of field trials to convince farmers that they're not going to get a decrease in yield. And all of our farm trials have come out positive, meaning they don't lose yield. And then sometimes there's certain ways you can use the bacteria. They're even seeing increases in yield by 20%. So it is being used, and it's being used at the farming level right now. And by the end of 2024, this time next year, it will probably be commercial.
In 2018, you had a Dr. Class Mexico Innovation Fund grant, and you and your Mexican colleagues set out to test this biofertilizer in a variety of crops in Mexico. Could you tell us about that project, and where does it stand now?
Yep. So you're exactly right. Part of the getting off the ground of this biofertilizer was Dr. Class. And we were doing trials on Harvard's campus. I had a little plot of land over here, and my student would go over and we were growing things, but only on Harvard's campus. So this is before the huge farm trials I'm talking about now in the United States. So in 2018, I just had a little plot of land over by Northwest Building, where the greenhouses are, and we were growing stuff. But we wanted to start doing bigger field trials. And my first collaborators were Mexican scientists, botanists, and they started doing larger field trials because they were plant scientists in Mexico. So, what I'll call our first substantial trials on growing plants were done in Mexico under the Dr. Class grant. And part of Dr. Class funded the plant biologists, and other part funded a young Mexican scientist who studied how nitrogen is changed into fertilizer mechanistically. So we had both like a field trial and mechanistic science being done in Mexico that gave us insights that kind of launched the project. It was the predecessor to all the bigger stuff that I just talked about. And it was fun. First, it was interesting because it was fun working with the Mexican scientists. And then secondly, it was interesting because it moved us beyond our little plot of land by Northwest building to something more substantial.
Where were you in Mexico?
So in the mechanistic studies, we were in Mexico City. We were at a university there. And then for the field trials, we were down south of Mexico City, where a lot of agriculture is done in Mexico.
And do you see this as a possibility to change, to transform agriculture in Mexico and in Latin America?
Yeah, I sure do. A company formed, there's big backers behind it, and we've done everything in the United States so far. And as I speak now, we're setting up agreements in Latin America and in Europe to begin field trials there, because even in those countries, they have all their federal regulators. Farmers are farmers. I don't care where they are, Latin America, Europe, or United States. They just worry about yield. And whatever they do, they don't want to have their yield go down. So we're going to start large farm trials in Europe and in South America and Latin America, because I need to get the confidence of all these different farmers. And the way you get confidence is you run big field trials, 400 acres, and then show that there's no loss of yield. With all the other benefits I just mentioned, they get excited to use it. So that's what we're doing now. I expect, maybe I'm being too optimistic, but by 2025, we'll be in Latin America and Europe.
What countries are you looking at?
Right now, Mexico is one, and then Brazil is another. And then in Europe, we're looking in Germany, and actually we're looking in Turkey. So the way this works, June, is kind of weird. I don't interact with the farmer directly. There are mid-level companies that deal with farmers. So we're dealing with the mid-level company who then has a network all through Europe and Latin America. And we'll use their network to do our field trials. So those mid-level companies that deal between, say, the fertilizer producer, which I would be with the bacteria, and the farmer, they have networks that extend all over. So I don't have to go to each country and do that myself. I go to this middle agency that already has all the regulation. They understand all the regulatory practices of all the different countries. It's a way for me to move really fast across a broad spectrum of companies in Latin America, South America, and Europe. And those agreements have all been signed already. That's why I'm saying by the end of this year, I'll be doing those cycles. And the reason why it's important, let's go to Latin America and South America, because winter's showing up in America now. And farmers don't grow in the winter, but it's summer as you go south. And so it allows me to do field trials year round.
Do you see this fertilizer as being equally useful for agro industry and for small sustainable farmers in Latin America?
Yep, because of what you said before, and I glossed over it. You said distributed. I don't need a big, large plant. You could think of it, if you've ever gone to a microbrewery and saw the silver tanks, I'll be able to make all the fertilizer for a large area with one of those type of architectures. I mean, It's different. The nuts and bolts are different than the beer fermenter, but it's on that size. A huge advantage I have, which is what you're bringing up, is I don't need a big fertilizer plant like BASF at oil refinery, because that's where they're getting all their high methane from. I literally am going to set up solar panels or use a green food source like green hydrogen. There are other green food sources which are distributed, and then I grow the fertilizer right at the farm. And by the way, we'll be able to grow enough not for one farm, but for a whole area of farm. So the way I see this is I just set up these little, what you can think of fermenters, like the beer fermenters that you see in microbreweries, and I scatter those around. And depending on how big the fermenter is, I could do a single farm or I could do a group of farms, and it would all be distributed.
Sounds like it's fairly easy to scale up with this type of fertilizer.
Yeah, exactly. Especially when you're doing things biologically and chemically. When you go, say, from 100 liters to 1,000 liters to 1,000,000 liters, you get all sorts of different problems that you didn't anticipate, like just taking care of heat. If I stir something in 100 liters, that's a lot different than stirring something in 1,000,000 liters. You can just imagine all that. But here, my scale up isn't getting bigger, which brings in new problems. I already have a 100-liter reactor working. I don't think I'll ever need to be over 1,000-liter reactor, even for big areas like many, many, many farms. And I already have those working. 10 miles south of Boston, there are all these reactors that we've done everything in. And I already know how they work, and they work perfectly. So the way I'll scale up is I'll put a 100-liter reactor there and there and there and there in a distributed way. And I never have to go and build the 1,000,000 liter reactor. I already know that the scale up works. So it's just putting the hardware in. That has this CapEx number, capital expenditure number, already in it, where I'm telling you that I'm cost competitive with nitrogen at the 100-liter and 1,000-liter scale.
So you're cost competitive. It does good things for energy. What kind of resistance or problems are you anticipating, particularly in Latin America?
So first, I need to get the federal regulations in Latin America, and each country has different regulations. I will tell you, they're more reasonable than the US. As usual, the US has all these weird regulations that are politically motivated, and they have all this other baggage. The ones in Latin America and South America, they tend to only focus on, is it going to hurt something or not? It doesn't have all the political baggage. So the regulations are usually more relaxed because I don't have a bunch of other secondary interests thrown onto the regulation that you do in the US. So I don't think that's going to be a hurdle. One thing that is true is I need to understand how the bacteria operates in different soil types. But that's why we do field trials. I have a learning curve that I need to get over to say, in this part of Mexico versus this part of Mexico, what is the soil like and how does the bacteria operate in those soils? But we've had to do that in the US. That's just the learning curve. So that's why I'm saying 2025. What I do here, I can't immediately assume in terms of how much stuff, how we lay it down. Will it be exactly the same? So I have that learning curve, which we'll just do. But the real barrier is the trust of the farmer. And the only way I get the trust of the farmer is to show them real data saying, look, I did this huge field trial and you are not going to lose any crop yield. And that's the only hurdle. And that hurdle comes with confidence. And the confidence comes from these field trials that we have to do. And then if that all works, there's no barrier. I mean, I can already tell you in America, there's lots of farmers who want this right now. And we were just waiting on the federal regulation. Now that we have it, we're good to go with the US farmer. So I expect the same in Latin America.
Does the type of crop make a difference?
Now, Each crop uses nitrogen. Nitrogen's nitrogen, nitrogen. So that doesn't change. But when a plant needs it and how much, things like berries need 3 times the amount of nitrogen than leafy vegetables. And then when do they need nitrogen? That we have figured out with different field trials of when does the plant need it? How much does it need? And it doesn't do it linearly. Like it might need a big burst at one time, then not much nitrogen, and then at a later growing period, a lot of nitrogen. And that varies from crop to crop to crop. But through all our field trials, that we have under control, with the caveat that different soil types make a little difference. Broadly speaking, we have it, but then we need to understand the soil type for each.
Are you planning to travel to Latin America this year?
Yeah, I probably will go down there. Certainly the people doing the big field trials, they are there during the field trials. So if it's not me, the people I work with, Harvard is part owner of this company. So that is driving the commercial piece. And I have a lot of engineers. I have a research group at Harvard and I do PhDs. And now I have a research group, which is the company, and they do more of the science and engineering of commercialization. You don't do that with PhD students. So that's why I keep everything separate.
So, on the ground, how much are Latin Americans actually involved in this process?
It's going to definitely be Latin America. The business model will be to train and set everything up in Latin America, and it will be the people there serving those farms that are running the reactors. I'm not going to have a bunch of Americans doing it. It's going to be all partnerships with different countries where they become the operators of that technology. So all these 100-liter reactors and 1,000-liter reactors and distribution, I'll do that with that country. And remember, I told you that middle organization, they deal with the people there. They don't take Americans and move them there. So yeah, that's all part of it.
Uh-huh. Sounds really game changing.
Yeah, I'm especially excited about how much CO2 I'm saving from going. I'm an energy person and I started my career first, how do I do renewable energy? And then how much of an impact can I have on the carbon footprint? And the real game changer here is first, it doesn't pollute the environment in terms of groundwater. And then secondly, I reduce enormous amounts of CO2 from going in the air. The sustainability of this type of thing really has me excited.
So, are you much more optimistic about these kinds of products than you are about the possibility of alternative energies at this point?
Yeah. I mean, I'm optimistic about fuels sooner or later. There was an article in the New York Times, but the green revolution is already happening under your nose. You just don't know about it. So that's happening. And by the way, everybody always thinks, oh, oil companies are going to be against what you're doing. And they really aren't. It's our decision as a population. In the 1900s, you built a massive infrastructure for coal, oil, and gas, right? And so that exists and it's paid off. The challenge is, how do you begin getting renewables into this? And that's what that New York Times article said. That's happening as we speak. But that's going to take longer because of the massive infrastructure around it that you got to supplant. For these other processes we're talking, those are smaller infrastructures that are easier to supplant. It's really just basic economics here that you're up against. And there's nobody at fault. Whenever anybody points their finger at an oil company, I always say, okay, then in your life, stop using it. And nobody's taken me up on that yet. They climb in their car and drive away. Now, are they to be blamed? No, they're just taking advantage of this massive infrastructure. So that change is going to be slower, but it is happening. With these smaller infrastructures, you can do it much more quickly. And sustainable fertilizers is easier to go after. And that's why I went after it. We still are going after the carbon infrastructure too, but we're realists. And that's why we chose nitrogen first, because it has a huge impact on carbon in the atmosphere and climate change.
Thank you for your time. This has really been wonderful. You've been listening to Daniel Nocera. He's the Patterson Rockwood Professor of Energy at the Department of Chemistry and Chemical Biology at Harvard University. He's well known for his work on renewable energy, and we've been really pleased to be talking to you about your latest project. Thank you, Dan.
Thank you, June, and thank you, Dr. Klaas, for getting me started.